Organic bentonite is manufactured by swelling and dispersing by purified bentonite and montmorillonite in water, and ion exchanging the exchangeable cations on the layer surface with quaternary ammonium. When the cations which required for montmorillonite to swell with water are modified to surfactants, it demonstrates hydrophobic tendencies, or tendencies of not mixing well with water. This is then evaporated, dehydrated, and pulverized in manufacturing. Regarding properties of organic bentonite, characteristics differ depending on the type of quaternary ammonium. Our company uses these 4 types of quaternary ammonium. As a general tendency, an organic bentonite modified by quaternary ammonium with a benzyl group is compatible with aromatics, and quaternary ammonium with several sterile groups is compatible with aliphatic solvents. In addition, quaternary ammonium with few alkyl chains tends to be compatible with solvents that have a relatively high polarity. In addition, compatibility can be achieved with a wide range of solvent types by changing the modification amount or modifying 2 types of quaternary ammonium. Our company performs this process at the Nihon Yugi Nendo Company Limited in Mie Prefecture. Organic bentonite manufactured in this manner is swelled and dispersed in an organic solvent, and thickening and thixotropy are generated based on the association structure. The characteristics of organic bentonite are that it swells and disperses in an organic solvent through ion exchange of the exchangeable cations with quaternary ammonium. There is an appropriate type and amount of quaternary ammonium according to the type of organic solvent. The particles that swelled and dispersed in the organic solvent provide thickening, and the dispersed particles generate thixotropy through reorientation. There is little effect based on temperature due to the use of inorganic minerals. Organic bentonite is manufactured by modifying the layer surface of montmorillonite extracted from bentonite with quaternary ammonium. For organic bentonite, the products are classified by the classification particle diameter, type of modifying quaternary ammonium, and modification amount of the modifying quaternary ammonium. Representative products include, for the S-Ben series, S-Ben, S-Ben-E, S-Ben-W, S-Ben N400, S-Ben-NX, S-Ben-NZ, etc., and for the Orgonite series, 2 micrometers or less, Orgonite, Orgonite T. Favorable dispersion is recommended in order to efficiently use organic bentonite. This is an introduction of the physical dispersion processing method and chemical dispersion processing method. A high shear processing method is one of the methods of physical dispersion processing. Higher viscosity is observed with higher shear processing in all solvents. An increase in viscosity indicates the dispersion is promoted. A heat dispersion processing method is one of the methods of physical dispersion processing. Higher viscosity is achieved by heating. An increase in viscosity indicates that dispersion is promoted. Next is an introduction of the methods of chemical dispersion processing. The addition of a polar activator is a chemical dispersion process. Polar activators that function as dispersants include 1. Alcohols, 2. Acids, etc. The addition of a suitable amount of a polar activator will act as a dispersant for organic bentonite. The recommended sequence of adding a polar activator is to add it at the same time as putting the organic bentonite in the solvent for dispersion, or to add it after putting the organic bentonite in the solvent. Please make the addition based on one of these sequences. If the polar activator is added to the solvent beforehand, the polar activator may be absorbed around the non-dispersed particles and become a cause of inhibiting dispersion. The function of the polar activator can be considered as follows. In nonpolar solvents, there is a condition where it is difficult for nonpolar solvents to penetrate in between organic bentonite layers by themselves, which generates difficulties for swelling. Regarding this condition, the polar groups of alcohols and acids in polar activators will attempt to develop hydrogen bonds with the oxygen atoms present on the crystallized end faces of montmorillonite, enabling interlayer penetration. This stimulates penetration in between the layers of nonpolar solvents, promoting dispersion. In this manner, materials that demonstrate hydrogen bonds will function as polar activators. When using alcohols as polar activators, alcohols with short hydrocarbon chains are effective, as the hydroxy group performs the function. There is a suitable additive amount regarding polar activators. A small amount would yield an insignificant effect as a dispersant, with low viscosity as a result. At a suitable amount, there is sufficient swelling, enabling effective dispersion through agitation, etc., leading to an increase in viscosity. If an excess amount is put in, the increase in solvent with a high polarity will begin to cause flocculation. There is an appropriate organic bentonite and an optimal amount of its polar activator for the solvent to be used. While there are various additive amounts of this polar activator according to the type of organic bentonite and type of solvent, an approximate optimal additive amount is around 1 mol per 100 grams of organic bentonite. With a favorable dispersion method and a suitable amount of a polar activator, organic bentonite will attain favorable dispersion and association and thicken in an organic solvent. In addition, here are additional examples of the effects that additional agents have on dispersion. As an anionic surfactant will adsorb onto the crystallized end faces and cap the portions that generate thixotropy, this causes gel disruption and decreases viscosity. This is sometimes used to promote dispersiveness and decrease viscosity. Non-ionic surfactants have a property where a part has a strong bond with water, causing water required for association to be taken away, decreasing viscosity. Similar to anionic surfactants, as association structures are not formed, it is sometimes used to promote dispersiveness and decrease viscosity. In order to use organic bentonite as a rheology control agent, it is necessary to perform separation and dispersion of the laminate layer of the organic bentonite in an organic solvent. In order to do so, it is effective to use an appropriate physical dispersion method and chemical dispersion method at the same time. Sufficient dispersion will generate thixotropy in the organic solvent. The paint drip test is an example of the effect of thixotropy. This shows something painted with paint using a comb-shaped implement, which is then stood vertically immediately afterward. As it flows down, the paint thickens in stages. The addition of organic bentonite grants thixotropy, controlling the dripping. Although these were examples, they show the general physical properties of S-Ben N400, which is an organic bentonite. Organic bentonite shows viscosity and thixotropy properties in an organic solvent, an anti-drip agent for paint ink, and pigment anti-settling agent, a lubrication agent for oil boring, a viscosity modifier for cosmetics, a viscosity modifier for cutting oils of brittle materials. These are some of the things it can be used for. In addition, organic bentonite is used in sealing agents, adhesives, resin additive agents, greases, etc.